So let us begin at the beginning. What is the real story behind Ptolemy, Copernicus, Galileo, Newton, Einstein, and the rest? What secrets lay hidden until now of the lives and thoughts of these icons of the modern world? As we shall see, everything is not as it seems. Nicholas Copernicus was a canon of the Catholic Church. He published a book around 1510 titled De Commentoriolus, advocating the heliocentric system, in which the Earth revolves around the stationary Sun. At the request of the Pope to fix the Julian calendar, a calendar which was increasingly becoming inaccurate as the centuries went by, Copernicus believed that his heliocentric system might be a more accurate timekeeper. By 1543, the year of his death, Copernicus finally published his second and more advanced book on heliocentrism titled De Revolutionibus Orbium Coelestium. Under advisement from his Lutheran counsel, Andreas Osiander, Copernicus presented his book to the Pope only as a hypothesis, not as a thesis or fact. There are two important things we should know about Copernicus's heliocentric system. First, in spite of the fact that Copernicus's name is often attached to the system in which the Earth revolves around the Sun, Copernicus was not its originator. It first appeared in the Greek school of Pythagoras around the 6th century BC, which was later advanced by its chief proponent, Aristarchus of Samos, in the 3rd century BC. Copernicus was merely trying to revive this ancient system. Other Greeks, such as Aristotle and Hipparchus, were devoted to the geocentric model.
The second important fact is, although Copernicus rejected Aristotle's geocentrism, he nevertheless believed in Aristotle's philosophy, especially that the circle was the perfection of shape and movement. Therefore, Copernicus sought to put the planets in uniform orbits, and do so by having them move through perfectly circular crystal tubes.
Here we see a page taken from Copernicus's book De Revolutionibus. It shows that he wrote the name of the planet inside each circle to represent Aristotle's original model that the planets were traveling in circular and transparent crystal tubes. Since today we know that the planets neither travel in tubes nor revolve in perfect circles, it is no surprise that Copernicus never succeeded in getting his model to work correctly. Copernicus tried to compensate for these difficulties by adding more movements to the planets. To do so, he added more circular paths to his original circles to make the movements of the planets more versatile and flexible. But even this remedy did not produce an accurate representation of what actually occurs as the planets move in the sky. As a result, Copernicus's model was more or less a failure, since it charted the planets' movements no better than its forebearer, Aristarchus. Copernicus's system was also no more accurate than its geocentric rival, the Ptolemaic system, which had been developed by Claudius Ptolemy in the 2nd century AD and had been the reigning model of cosmology for the 1200 years prior to Copernicus. In fact, to bring his model close to the accuracy of Ptolemy's, Copernicus was forced to add more circles to his model than Ptolemy had in his model. Today we know these extra circles as epicycles, from the Greek word epi, which means upon, and cycle, which refers to a circle. In his first book, De Commentoriolus, published in 1510, Copernicus was already forced to use 34 epicycles. By the time he published his final book in 1543, he realized that the motions of the planets were much more complex, and thus he was forced to add 14 more epicycles for a grand total of 48 epicycles, which was 8 more than Ptolemy's model. Ptolemy understood that the Greek cosmological models, whether the heliocentric of Aristarchus or the geocentric of Aristotle, were rudimentary, and thus could only provide general movements of the planets. Ptolemy discovered that planetary motions were much more complex than what circles could represent. To compensate for this difficulty, Ptolemy invented 2 geometric devices. The first, as we have seen, was the epicycle, which even Copernicus himself used for his heliocentric model. Ptolemy's second invention, which was the greatest achievement of astronomy in the first millennium, was the equant. The equant allowed the planets to move in non-uniform orbits so that the speed of the planet could vary. In fact, as we shall see, Ptolemy's equant-based orbits were the forerunner of Kepler's elliptical-based orbits. Both artifices accomplished the same purpose, creating non-uniform orbits for the planets to match their erratic movements in the sky. The problem with Ptolemy's model, however, is that it was not equipped with accurate distances between the Sun and some of the planets. As a result, Ptolemy placed Mercury and Venus in the wrong position relative to the Sun, and Galileo later noticed this problem when he saw the full phases of Venus through his telescope. Full phases which Ptolemy's model could not produce. Ptolemy was quite clever, however. He left 6 variables so that in the future his model could be adjusted when the correct distances became known. Although Copernicus, as we noted, had problems of a different nature, still, he did not need to know the exact distances to the planets. His model only required him to know the order of the planetary orbits, and for the heliocentric system, this was known since ancient times. As a result, Copernicus's model had no problem showing Venus's full phases. This was one of the reasons Galileo promoted Copernicus's model as being superior to Ptolemy's. Galileo reacted against Ptolemy for another reason. Ptolemy's model had the Sun, which was known to be larger than the Earth, revolving around the smaller Earth. To Galileo, this seemed counterintuitive, especially since he had witnessed in his telescope that small moons were revolving around the larger Jupiter. Galileo believed that the smaller Earth should be revolving around the larger Sun. This was a lingering objection to the geocentric model. We will see the outcome momentarily. A major development occurred for the heliocentric system that made a vast improvement over the crude and unworkable model of Copernicus. In order to account for the irregular movement of the planets, Johannes Kepler dispensed with Copernicus's circular orbits and instead put the orbits of the planets in ellipses. This adjustment allowed the planets to travel at non-uniform speed, just as Ptolemy had accomplished with his equant a millennia and a half earlier for the geocentric system. The planet orbited in an ellipse around 2 foci, with the Sun occupying one of the foci. So instead of using Ptolemy's equant, Kepler made the Sun one of the 2 focal points around which the planet would revolve. The result was that when the planet was closer to the Sun, the faster was the speed of its orbit. The farther away, the slower the orbit. So close were Kepler's ellipses to that of Ptolemy's circle with an equant that we can superimpose one on the other and see the similarity.
In the battle of which system was correct, the heliocentric or the geocentric, Tycho Brahe, the famous Danish astronomer, presented a perfected model of the geocentric system. Tycho did 2 basic things. First, he inverted the Copernican model. Although he still allowed the planets to revolve around the Sun, he made the Sun revolve around a fixed Earth. As such, the Earth was no longer a planet.
In this way, the Tychonic model kept the geometry and distances that Copernicus had employed. The only difference was that the Earth was the center of the whole system instead of the Sun. By doing so, Tycho also corrected the Ptolemaic model, since Mercury and Venus were now at their correct positions from the Sun. As we can see from the animation depicting the orbit of Mars, the distances and relative movements of the 3 systems are equivalent. Although Tycho's model did not use either elliptical orbits or an equant, if such a modification had been applied, it would have made his model just as accurate as Kepler's. As one physics course from the University of Illinois put it, quote, "One could also construct a Tychonian model with elliptical orbits," unquote. This modification was, in fact, added to Tycho's model by Giovanni Riccioli in his 1665 book Astronomia Riformata. And after Riccioli made this modification, he remained a devoted geocentrist. For reasons that were more philosophical than scientific, Kepler did not want to promote Tycho's new geocentric model. Kepler highly valued the Sun as the centerpiece of the cosmos, whereas Tycho sought to preserve the ancient astronomy from Ptolemy that had the Earth in the dominant position. As is often the case in science, one's philosophical views invariably influence his interpretations of the scientific data. Hence, after Tycho died, Kepler made arrangements to obtain Tycho's 40 years of planet charting that was originally meant to support the geocentric system, and he used it for the heliocentric system. This wasn't hard to do, since, as we have seen, the models were geometrically and mathematically equivalent. As world-renowned physicist George F.R. Ellis notes,
"I can construct for you a spherically symmetrical universe with Earth at its center, and you cannot disprove it based on observations. You can only exclude it on philosophical grounds. In my view, there is absolutely nothing wrong in that. What I want to bring into the open is the fact that we are using philosophical criteria in choosing our models. A lot of cosmology tries to hide that."
Following Kepler, Galileo also rejected Tycho's model. Perhaps this was because in Tycho's model, the large sun was revolving around a small Earth, the opposite of what Galileo intuited when he saw moons revolving around Jupiter.